All right, good evening, everyone. So we want to have the continuation of our class on sequences and series. And hopefully in this class, we can exhaust everything on geometric series and then move on to harmonic sequences. In our previous class on sequences and series, we had our conversations around the basics around arithmetic progression, where we talked about the general term of an AP, and we specify that to be a plus n minus 1 times d, a plus n minus 1d. And then we also talked about the sum of the n terms of a particular arithmetic progression, where we took that as n over 2, 2a plus n minus 1, and we're able to use these formulas in several questions. The applications of each and every one of these formulas, we were able to resolve questions on the arithmetic progression. In this particular tutorial, we want to dwell majorly on geometric progression. Now, this is very similar to arithmetic progression. One of the similarities is the fact that we also talk about the first term of a geometric progression in terms of A. So the very first term of a GP is A. That's the first term. U1 in a GP is A, which is the same thing as that of an AP. Now, what the difference between an AP and a GP is that whereas in AP we talk about the common difference as D, in GP we talk about a common ratio. And here we specify it as R. Now, quickly we can talk about how we're going to identify the different terms of an AP and GP. Now, but we'll be talking majorly on that of a GP in this particular class. For that of a GP, the very first term, as I said already, is termed A. Whereas the second term is A times R. The third term is A times R raised to power 2. And the fourth term, you can assume what that will be. That will be A times R raised to power 3. Now, let me show you quickly the understanding of this whole thing we wrote here. Let's take, for instance, we had a GP of this form: 2, 8, 16, no, we would have to have 32 here. Now, if you can notice, this is a very good example of a GP, because one of the things that goes on with a GP is that you must have what we call a common ratio. And the use of the word common here is because we're going to be having an identical situation around each and every one of the terms. So in this case, now you can see that what we have here was 2. Now, if we multiply 2 by 4, we got 8. If we multiply 8 by 4, we got 32. If we multiply 32 by 4, we got 128. So you can see that's why it's called the common ratio. It's common to every one of them. Once there is maybe the same ratio between one or two, and it doesn't occur in the next one, then that's not a GP. One of the things that defines a GP is that it must have what we call a common ratio. And that common ratio must be common. It must go on from the first to the very last term. Now, let's quickly look at what's going on here. So I had a first term as 2. When I wanted to do the next term, knowing that my common ratio was 4, when I wanted to do the next term, I said 2 times 4. Of course, that gave me my next term, which was 8. When I wanted to do the term after that, notice I did 2 times 4 times 4. That means whatever was the second term, I multiplied by 4. That was how I got 32. And then the next term I had 2 times 4 times 4, this was the third term. Then I multiplied by another 4. Of course, 2 times 4 times 4 was 32. And you saw I got 128. Now, this is the basis on which we're able to establish these particular functions we have here, where we have the first term as a, the next term as a times the common ratio, the next term a times the common ratio. It's more like, this is more like writing a times r times r. Obviously, r times r is r squared. And then that's what we had here. Then the next one is a times r times r times r. That was how we got r cubed. So this is the basis of which we're able to talk about the common ratio, the terms of a GP. So we have the first term given as a every time. The second term will be a times r, ar. The next term will be a times r squared. You need to master the model at which this moves. And then you can go on to, for instance, if I ask you, what is the 10th term? Well, the 10th term obviously will have to be a times r raised to power 9. You can notice the logic around it, that when we had the second term, it was r raised to power 1. When we had the third term, it was r raised to power 2. When we had the fourth term, it was r raised to power 3. Obviously, the 10th term will be r raised to power 9. And you can go on to infuse that into any particular term. The 100th term of a GP will be a times r raised to power 99. So it's the same format everywhere at all time. All right, so this is the first basis I want you to be reminded of when you're dealing with GP. Now, the next thing to pay attention to is what we call the general term of a GP. Now, from what we just wrote right now, we can generalize and make our general equation of a GP un. Of course, this n signifies the particular term. If it was the first time to be u1, second time will be u2. But if we have n, of course, we're trying to make a general assumption here. Un will be equals to a r. Notice the logic. It's always whatever n was, it was 1 less than whatever n was. You can see when it was second term, it was raised power 1, third term raised power 2. So un will be ar n minus 1. So this is how we got this is how we're able to get the general term of a GP. So you need to note that this is very important while solving questions. Now, we also need to talk about some other things, which is very vital to solving questions, which is the sum of terms of a particular GP. The sum of terms of a particular GP. So let's talk about the sum of terms. How do you find the sum of the first terms of a particular GP? Well, I believe I gave a bit of that in our previous class. When you're dealing with sum of terms in GP, we have two different formulas to identify with. The very first one will pay attention to the fact that at times we may have our ratio less than 0. So because it's not the common ratio in a GP sometimes could be greater than 0. So sometimes we could have r less than 0. Sometimes we can have our common ratio greater than 0. Cases, of course, less than 0 is if we have, for instance, our common ratio being minus something, maybe minus 1/2, for instance, e.g. minus 1/2. In this one, greater than 0, we can have situations like 1/2. We can have situations like 2. We can have situations like 4, and so on. It could be any number as long as it's greater than 0. Now, looking at this now, we have different formulas, of course, very similar, but different formulas you use depending on whatever your ratio is. So in the case where your ratio is greater than 0, the sum of terms, which is the sum of the very first n terms of a particular geometric progression, is given as a r raised to the power n minus 1 over r minus 1. You need to take note of this because this is some of the formulas you'll be using while solving questions under geometric progression. And for that one, we have, sorry, this formula I gave you is for when r was greater than 0. I need to state that this was for when r was greater than 0. And when you have r less than 0, the formula will be similar but not exactly the same. We will have a into 1 minus r raised to the power n over 1 minus r. This is for when we have r to be less than 0. All right. So these are some of the very vital formulas that you have to note when dealing with geometric progression. Now we have another formula you need to pay attention to, and that formula is for when you have the sum to infinity. So you could be given a question and you could be told to find the sum to infinity of a particular geometric progression. When you have a case like that, the formula is quite simple. You just have to use this formula. That's a over 1 minus r. And in this case, your r is mostly expected to be less than 0. Now let's try and solve a couple of questions. I believe we solved a question already before, but let's just try and solve some other questions to solidify our knowledge on geometric progression. All right. We have this particular question I would love us to solve. We are told that we have three numbers in a GP whose sum is 10 number 1 over 12. Just so you get the idea of this, we have three numbers in a particular geometric progression. We're told that the sum of those three numbers, if you have to take the question down, unless you can put it down somewhere. The question is find three numbers in a GP whose sum is 10 number 1 over 2 and their product is 27. Find three numbers in a GP. It's quite a very interesting question. Find three numbers in a GP. I think you need to pay attention to this particular one. And this question is going to give you an insight into how to generally tackle questions on GP, because this is some of the kind of questions that you see in your examination. Find the three numbers in a GP whose sum, the sum of this number is 10 number 1 over 2 and their product is 27. So find three numbers in a GP whose sum is, find three numbers in a GP whose sum is 10 number 1 over 2 the sum is 10 number 1 over 2 and their product is 27. The sum of the numbers will give you 10 number 1 over 2 and the product of these three numbers will give you 27. This is quite an interesting question. Very interesting in the sense that it tests your ability to understand all these concepts we talked about on geometric progression. All right. So let's try and see how to tackle this quickly. How do you tackle questions like this? Of course, if you recollect when I started this class, I said you define terms in a GP based on the first term and a common ratio. So for if you had three consecutive numbers, if you have three numbers, of course, you know that you can assume for simplicity, of course, it's not going to be. I want you to understand that the approach we'll be taking is actually for simplicity. There are other approaches you will take that will still assume the same answer. But for the sake of simplicity and just for every layman to get a very sound understanding of it, what we're going to do is to assume that those numbers are the following. So we're going to say, let's say the first number, the second number, the third number. So we're going to say the first number is A, the second number is AR. Of course, if they are numbers in a GP, we're expecting them to have the same, a common ratio. And if this was the first or the second, then this would be the third. Of course, why not? So you can understand what we just did. So you're told now that the sum of these three numbers gave you 10 number 1/2. Of course, when you're solving word problems, you want to bring out all your values, all the values in the expressions. So they said find three numbers in the GP whose sum. So if they told you that the sum is 10 number 1/2, you want to say U1 plus U2 plus U3 equals to 10 number 1/2. That's like a basic step you should always do. The next thing to do is to try and now convert this. This was just written in terms of numbers. Then you go on to now express it in terms of a GP, where you can have it as A plus AR plus AR square equals to 10 number 1/2. Of course, if you go on to do this, you'll be getting, you can easily factorize A from here, and you'll be having A into 1 plus R square equals to, this would be 21/2. So whenever you're solving questions like this, take it bit by bit. You don't have to rush or assume you don't know it. Just do whatever you can do at that instance and stop right there. So what we have now, I've been able to interpret the very first expression that says whose sum is 10 number 1/2. All I did there was just say these are the three numbers and this is their sum, and I expressed it in terms of a GP. This is their sum. What else could I do in this line? I could see that, okay, A is common to the three of them. I could factorize that out. I did that, and then I stopped there. So you can put this somewhere, and have this somewhere. Later on, you will be using it. So the next thing to do is, because one of the reasons why you have one of the ways to examine question is always to make sure you exhaust all that was told to you. So you're told that the sum is 10 number 1/2. But you are also told that the product is 27. So you have to also deal with the product being 27, which is quite very, very important. So let's see. If the product is 27, that means I can easily say U1 times U2 times U3 equals to 27. Of course, that's what they said. This is not me doing anything other than just interpreting the question. So the product is 27, so I can write it like this, and I can go on to write it in terms of a GP. I can write it in terms of a GP where I make use of my terms. That's my A times AR square equals to 27. So if you do this, you'll be having A cube times R cube equals to 27. I'm sure you can all agree with that. A times A gives me A cube. R times R square gives me R cube. So looking at this, I have A cube R cube equals to 27. Now, I'm sure we all understand the law of indices, and I wouldn't be wrong if I go on to write this as AR, everything raised to power 3, equals to 27. I can go through different routes here, depending on whichever I want to choose. Just for the sake, let's just flex a little muscle on indices. For those of you that probably, I'm sure you're enjoying indices, you would understand what I'm trying to do here. I can go on to write this as AR raised to power 3 equals to 3 raised to power 3. and go on to say I'm going to cancel, which is a law of indices that permits me to cancel this particular thing. I'm sure you agree with me that that's permitted. So if I do that from this place, I can get my AR to be equals to 3. Now, whichever one I decide to hold accountable, I can decide to hold A accountable or R accountable. But I'll prefer to hold, don't forget that I have my equation, a particular equation here that I stored somewhere. Don't forget, this is what I'm going to be using. You see, why I told you that when you have a question like this, you don't want to be in this, you don't want to fret on maybe you know it or not. Just do whatever you can do. I did this, I got this formula, I left it here. Now I've gotten something else that I can probably make use of. So I can decide now if I want to use A. That means I can say A equals to 3 over R and take that 3 over R and put it as A here. Now that's okay, that's good. I'm fine with doing that. Or I can decide to go on to solve for R and say R equals to 3 over A and take 3 over A and put it for R. Whichever direction you move through, you would always get your answer. So you don't have to be rigid about any approach. You just need to solve confidently. So for the sake of why not, I will just go on to do A equals to 3 over R. That's my own decision. It's not based on anything. It's not based on any other thing other than a decision I'm making. Like I can make the other decision and I'm deciding to move through this because this is the way that this has been solved before. So I want to just flow through this route for the sake of doing it. That's all. And again, I said I wanted to flex some muscles in indices. We can go on to do something else here where I can have AR cube and decide to move through the route of using my cube root. So I'll put a cube root to both equations and to both sides of the equation. 3 we cancel the cube root here, and this one will give me 3. So AR was going to be equal to 3. Of course, it's still the same thing. I just wanted you to know that you can move through different routes if you want to. So ultimately, AR equals to 3. So I'm going to get my A to be equal to 3 over R. I think that one is clear to everyone. So the next thing to do now is to put in this value as 3 over R into my other equation, the first equation I got, which I told you to keep in handy because it's quite very important. Now that I have that, I can go on to fix my A being 3 over R. So look at what I'm going to do. A is 3 over R, so I just want to have 3 over R, and I have 1 plus R squared equals to 21 over 2. I think everybody can do this. This is quite simple. This is just substitution. I'm substituting the value of 3 over R into that position. So what else do I have to do now for me to get the values I'm looking for? Of course, I'm sure you all agree with me that I can make do of cross multiplication at this very point because I have, of course, it's very, very perfect doing that. I can do that, and that's so nice to do. So I take R to multiply 21, I will have 21 R. I take 2 to multiply 3, I have 6. 6 times 1 plus R squared. That's just simple. Of course, but let me quickly tell you, for those of you that may be wondering what's going on here, if I had multiplied 3 with all the brackets here, with everything inside the bracket, then I would have to use 2 to multiply each and every one of them. But since the bracket is still safe, I just use 2 to multiply 3, knowing fully well that in this particular next step now, I will have to now use 6 on all of them. So anyhow you decide to move through, you will still get your answer. There's no pathway that would not get you to the right answer. So I go on to expose my bracket next. I have 6 plus 6R plus 6R squared. Of course, I'm sure you can already see what's going on here. This is looking much like a quadratic expression. Actually, not looking much like this is a quadratic expression already. So I'm going to have try to put it in a way that looks more quadratic. 6R squared. I have plus 6R. I have minus 21. I have plus 6. You see how did I get minus 21? I fixed, sorry, minus 21R. I brought in everything to this side because that's the obvious thing to do when you have a quadratic equation. You want to bring everything to one side and make the highest power as the first term, the next power as the second, and so on and so forth. I'm sure you understand that. So this is 6R squared. This will give me minus 15R plus 6 equals to 0. Now I have a quadratic expression. This I always want you to get to places like this. You're already very sure that you're on the right pathway. So what you want to do next, obviously, is to solve quadratically, and you have to look for the factors that, of course, we have 6 here. We have 6 here. So we're looking for something that can give me 36. 6 times 6, obviously, that's 36. Something that can give me 36 on multiplying them together. And when I add them together, I'm going to get minus 15. So if you can think very quickly, you'll see those two things are going to be minus 12 and minus 3. So I can dissolve this into 6r squared minus 12r minus 3r plus 6 equals to 0. Of course, now that I've done this, I can go on to factorize rightly. Oh, okay, I think I've used that. Don't forget, a is 3 over r. Let me leave that there so that, because we'll still be needing it, obviously. Once we are able to get our values, you can see that our quadratic equation is in terms of r. So obviously, my answer is going to be giving me that my r value. I'll be getting r as something and something. And you can see that my a value will obviously be gotten straight up once I'm able to get my r value. So if I try to solve this, I'll see clearly that, of course, this will give me 6r into brackets. I'll be left with r minus 2. And then I'll be having minus 3 into r minus 2 equals to 0. I'm sure you can see that. So I'm having 6r minus 3 and r minus 2 equals to 0. Of course, I know my r here will be equals to 3 over 6, or r being equals to 2. I'm sure everybody here can flow with what I'm doing there. Your 6r minus 3 equals to 0. That means 6r will be equals to 3, and then r will be equals to 3 over 6. That's how I arrived there. And then here, r minus 2 equals to 0, r equals to 2. Of course, that means my r is equals to 1 over 2 or 2. All right, perfect. Now we've gotten our values for r. Don't forget, the question was for us to find the three numbers in a GP. And don't forget, the three numbers we assumed was a, ar, and ar squared. So, of course, once we get our a and our r, we're good to identify the three numbers. So now I've gotten my r to be 1 over 2 or 2. Let me tell you what's going to happen here. I'm going to decide to use any of them. Once you use, for instance, let's say I'm going to use 1 over 2. Let me decide to use 1 over 2. If I use 1 over 2, of course, if r is 1 over 2, if r was 1 over 2, my a would be equals to 3 divided by 1 over 2, because 3 divided by r, if r was 1 over 2, that would be 3 divided by 1 over 2. I want you to always know how to make use of the division symbol like this, because, of course, some of you will want to write 3 divided by 1 over 2. Of course, that's correct, but obviously, you will do better by writing it this way. Having it, that means 3 divided by. So, because in this case now, I can easily write 3 times 2 over 1. I'll give you my value of 6. So that means when r was 1 over 2, I will get my a to be 6. Good. So I'm going to stick to that. And if I got r to be 1 over 2, that means my a was 6. So my three values now, my a was 6. That means my very first number is 6. The second number, let's try and find the second number. Don't forget, r, in this particular case, we're using r was 1 over 2. So my second number will be 6, which is a, times r, 1 over 2. And then my third number will be 6 times 1 over 2 squared. It's just that way. So looking at what we have here, you can see that my first number will be 6. My second number will be, this will give me 3. And my third number will give me what? My third number will give me, that will be 1 over 4. 1 over 4 times 6. That will be 3 over 2, because this will be 6 over 4. 6 over 4, which is the same thing as 3 over 2. So 3 over 2. So you can see, when I got r to be 1 over 2, my three different numbers, the three numbers in this GP was 6, 3, and 3 over 2. Now, you would say, but it's not only 1 over 2 I got. I actually got r as 2 also. Now, what happens to that r being 2? Well, just be calm. You're still going to get the same thing if you use r as 2. The major thing when solving questions on GP is you have to, number one, know all your formulas. And number two, be very confident when solving, because you will need to interpret whatever question you're given based on all your facts that you have known in terms of GP. Now, if I had r as 2, if r was 2, of course, if r was 2, then don't forget a was 3 over r. So a would be equals to 3 over r. And now if r was 2, that means a was 3 over 2. That means in this particular case, my first term will be 3 over 2. Now, if my first term is 3 over 2, my second term, don't forget, these were the three numbers. If my first term was 3 over 2, my second number will be what? Of course, 3 over 2 times r. 3 over 2 times a, which was the first term, times r. R was 2, so you have 2. Then my third term will be a, which is 3 over 2, times r square. That will be 2 square. Of course, you'll be having 3 over 2. 2 we cancel 2 here. Of course, the 2 here we cancel the 2 here. So we'll be left with what? 3. And in this particular case, you can obviously see that when you have 2 square, one of these square we cancel one of these, you'll be having 3 times 2 left. So your last term here, the third term will be 6. Now, if you look at this, you can see that it's the very same thing. The only difference is the arranging. So if you were using r as 2, the first term was going to be 3 over 2, the second term was going to be 3, the third term was going to be 6. If you used r as 1 over 2, the first term was 6, second was 3, and the third was 3 over 2. Anyhow you write this, you are all perfectly correct. So it's no difference if r was actually 1 over 2 or r was 2. So this is how you solve questions on GP. Most importantly, you have to solve it very confidently. So I want you to take this as something you will solve possibly later, and if we have time, we probably will solve it here later, but it's very similar to what we just did. Can you find 3 terms? Probably you can just write it somewhere. Can you find 3 terms? I want to quickly get into geometric mean, but I'll give you this question. You can solve it on your own, and if we have time, we'll still solve it in this particular class. Now, you're supposed to find 3 terms, 3 numbers rather, of a particular geometric sequence whose sum, now in this case, the sum is 28 and the product is 512. This will give you a very perfect practice for what we just solved. So you're supposed to find 3 terms in a GP whose sum is 28. So the sum here is 28 and the product is 512. So the very same format of questioning, you just have to follow the same process. Of course, this will give you a very great opportunity to practice what we've just done. Once again, you need to solve confidently. So find 3 numbers in a GP whose sum is 28 and the product is 512. I would I would love you to, if you can start solving right now, it's good. And before the end of this class, I will ask you of your answers. So let's quickly run into geometric mean. Very important aspect of geometric sequence. So when we talk of geometric mean, don't forget we discussed arithmetic mean when we were solving AP. When we're dealing with AP, we talked about arithmetic mean. On the arithmetic mean, I gave you the understanding of what to do each time you are asked to solve questions around that. And I also told you that you could be asked to insert arithmetic mean between a particular arithmetic progression. So I should be sure that you have probably taken this question down, so we can use the whole of the board. All right, let's talk about geometric mean. This is a very vital part of geometric progression. Geometric mean. All right, so what and how do you recognize the geometric mean in a particular sequence? Very, very simple, very, very straightforward. We have different, okay, I'm going to actually use the last result we got. Don't forget, this was the last result we got. We got 6, 3, and 3 over 2. Thank you. 6, 3, and 3 over 2 were three particular terms of a particular geometric sequence. Good. Now, if you are told to find the geometric mean of 6 and 3 over 2, if you are told to find the geometric mean of 6 and 3 over 2, your response will be the answer is 3. So once you have consecutive terms of a particular GP, if you have 3 consecutive terms of a particular GP, the middle value will always give you the geometric mean. Don't forget, when we're doing that of an AP, we said the geometric mean between, if we had, okay, let me try and do a revision. Can anybody tell me what I said was the formula for finding the geometric mean between X, Y, and Z? What's the arithmetic mean in this particular arithmetic progression here? Let me see, because I want to find a way to relate arithmetic mean with geometric mean. What's the arithmetic mean between this? Of course, if you have forgotten, let me remind you, the arithmetic mean is actually Y. It's actually also the middle value. So in this particular case, what you have to do, what we did here when we wanted to find Y, we said Y was equals to X plus Z over 2. This was when we're dealing with arithmetic progression. Don't forget, under arithmetic progression, we deal with common difference. But now, under geometric mean, it's still the same thing in terms of how to identify the geometric mean. It's always going to be the middle value also. But how you are going to relate to getting that middle value is going to be different. Now, for that of an AP, we said arithmetic mean between X, Y, and Z. If you wanted to find arithmetic mean between X and Z, we said it was going to be the middle value. And the middle value was going to be the sum of the two values, the one before and the one after, divided by 2. Now, but for that of a geometric mean, that's not the way it operates. If you want to find the geometric mean between two values, what you have to do is find the square roots of, so let me just write it this way. If we have, generally, in general terms, we have X, Y, Z as a particular 3 consecutive terms. The geometric mean will be given as Y. Obviously, the geometric mean between X and Z is Y, and Y will be expressed in terms of square root of X and Z. I want you to note this very carefully, that the geometric mean between two values is always the middle term, and it's gotten by getting the square root of the product of X and Z. This is just what it is. So in the case where you're not given Y, what you want to do is to find the square root of the product of these two values. So let's quickly run through some things, and then you understand much deeply how to find the geometric mean. Now imagine we have this particular geometric sequence, 3, 6. Imagine we have 3, 6, 12, 24, and 48. First of all, just to remind you, I'm sure you can always easily identify what a geometric sequence is. Because when you want to identify a geometric sequence, one of the things that will be seen there is that you'll be having a common ratio, not difference. That means in geometric sequence, you don't add values. You don't say 3 plus 3, you don't say 3 plus 2. It has to be a multiplication happening there. So in this case, now you can see that if you were not very, imagine you didn't know this was a geometric sequence now, you may want to start by saying, oh, 3 plus 3 is 6. Okay, 6 plus 3, because of course it has to be a common difference. 6 plus 3 is not 12. Of course, 12 plus 3 is not 24. So you can see that a difference is not happening here. Addition is not happening here. But let's go on to find a way to know if this was a geometric sequence or not. 3 times 2 is what? 6. 6 times 2, 12. 12 times 2, 24. 24 times 2, 48. A multiplication is going on there. So obviously this gives me my conclusion that this is a geometric sequence. All right, now let's get back to geometric mean. How do you understand geometric mean. If you're told to find the geometric mean between 3 and 12, of course, you can see already that I told you that if you have it in this form, the geometric mean will be the middle value. So obviously, I know that 6 will give me my geometric mean. But let's now go on to calculate it. Let's assume we do not know it. Let's assume x was inserted here. Let's say we were told that this was x and I did not know it. How do I get it? What am I going to use? Of course, I told you already that you use this format where you go on to find the product and then you find the square root of that product. So what you have to do here to find x, of course, x will be equals to the square root of 3 times 12. What's the square root of 3 times 12? That's 36. What's the square root of 36? 6. Did we not get the same answer? Of course. So you can see that that's the perfect way of getting the geometric mean of 3 consecutive values in a sequence. All right. Now let's try a bigger one, a larger one, and let's see if it works for that also. So let's say, for instance, we're told to find a geometric mean between, not 3 and 48, but between 3, sorry, not 3 and 12, but between 3 and 48. Let's see if this is going to work. Of course, let me try and answer this without solving that. How do you find the geometric mean between values? I said it's always going to be the middle value, all right? So if I was going to find this without having to work anything, I'm going to check for the middle value between 3 and 48. The middle value between 3 and 48 is obviously 12. So that means my geometric mean by observation, not by calculation, of course, has to be 12 because that's the middle value. So 12 gives me my geometric mean. But let's go on to assume that what I had here was probably y. Let's say, for instance, I wasn't told the value here, and I was just told to find the geometric mean between 3 and 48. So what am I expected to do? Of course, you follow the same pattern. Y will be equals to the square root of the product of the two values you are talking about, the two values you're trying to insert or to get the geometric mean between them. In this case, we have 3 times 12. Sorry, I said 12. 3 times 48. Because we're dealing with 3 and 48 here. So how do we go on to do this? Of course, you can punch this on a calculator, but an easier way to do this, in case you are wondering, if you don't have a calculator and you want to work this same thing, you can easily just make use of your understanding of sorts, and you know that this would be square root of 3 times, of course, I believe 48 is that'll be 3 times 16. Am I right? 48 is 3 times 16. So this is me breaking. Sorry, did I say 3 times 16? 9 times 16. No, it's actually 3 times 16. It's actually 3 times 16. This now gives you 9 times 16. So 3 times 16 is actually 48. So breaking 48 down 3 times 16, of course, gives me a better way of handling this, because I can see that 3 times 3 now is going to be square root of 9 times 16. And I'm always very delighted when I'm seeing numbers that are perfect square inside the square root, because I know that this obviously gives me an easier way of tackling this. So when I see perfect squares, which I'm sure you all know what perfect squares are, when I see perfect squares like this, 9 is a perfect square, 16 is a perfect square. Of course, I'm delighted seeing it under a square root, because I can easily go on to now make it like this: square root of 9 times square root of 16. Square root of 9 is 3, and square root of 16, 4. So my answer here is 12. Of course, don't forget we're trying to find y. My y here is 12. So can you see how nice this is? I've been able to get my value of y to be 12, which was 12 before. So you can see from all I've been saying, you can actually find this by observation or by calculation, whichever way you're going to get your answer. So I think this is the understanding I would love you to have on geometric mean. This is how you solve geometric mean under sequences and series. Now, there's a particular question I would love us to solve. And before we start thinking about closing up for this class, of course, I gave you a question already. I would love you to solve that. I want you to try and look at this particular question and how much you can. This question will actually shake some tables, and actually for those of you that you are interested in success, I want you to know that this is a 2019 question. This question came out 2019, so you understand that this is A-level standard. So, and these are the kind of things you should be ready for. It's not an abstract question, it's a very practical question. So let's try and see if you can solve this particular question. We're going to solve it together. It's a past question. Now, let me quickly get your feedback on the class so far. How much and how well are you grasping the things we're solving? All right, this is a question I have to rub the whole board off for because it's quite solid. It's very simple, but it requires your ability to think and to understand fully both AP and GP. So this question will test your understanding of all the things we've been doing so far, starting from AP up until GP. All right. Okay, you know what I'm going to do? Okay, let's solve this question. Then after this question, we'll take a few minutes after to talk about harmonic sequence. But let's solve this question very quickly. It's a very vital one. All right. This is the question. An AP has a common difference of 2. An AP has a common difference of 2. All I'll be doing is to just write, I'll be bringing out my interpretations in front of every one of us. So we're told that an AP has a common difference of 2. So I can write that D equals to 2. And I was also told that a GP has a common ratio of 3. A GP has a common ratio of 3. So from this AP now, my D is 3, or 2 rather, and the common ratio for a particular GP, common ratio now, is 3. So look at now, we're talking about both common difference and common ratio in the same question. All right. Now, they said the corresponding terms are added together to form a new sequence. Please pay attention very carefully to this question. We have an AP. The AP has a common difference of 2. The GP, we have a GP. The GP has a common ratio of 3. They then told us that there's a new sequence that was going to happen as a result of these 2 parallel sequences. Parallel in the sense that the one is an AP, one is a GP. They said the corresponding terms are added. The meaning of corresponding there means first term of AP plus first term of GP will form the first term of the new sequence. So that's the meaning of the corresponding terms. Corresponding in the sense that if you had term 1, you know what we're going to do? We're going to try and say the terms of the GP, we'll call it U. So U1 plus U, we'll call the terms of the GP, sorry, the term of the AP will be U, the term of the GP will call it T, just for the sake of making the right differences. So they said U1 plus T1 will give us the new sequence V1. So just for the sake of context and for everybody to be able to flow with this particular question, U1 here represents the terms of an AP, T1 here represents the term of a GP, and this V1 is the new sequence. Please pay real attention to this question so you can understand it clearly. So they said an AP has a common ratio of 2 and a GP has a common ratio of 3. The corresponding terms, of course, of the AP and GP are added together to form a new sequence. So if I wanted to get the second term of the new sequence, I will go on to add the second term of the AP with the second term of the GP. It will give me the second term of the new sequence. If I wanted to find the fifth term of the new sequence, I'll go on to get the fifth term of the AP with the fifth term of the GP. That's what's going to give me the fifth term of my new sequence. All right. Now, you now said if the first term of this sequence, this new sequence, the first term, they said the first term of this new sequence is 8. That means they said V1. That means I'm using V to represent my sequence, my new sequence. So they're telling me now that V1 was 8. They said the first term of this sequence is 8 of the new sequence, and the third term of this new sequence is 52. That means V3, the third term, is 52. Now the question now said we should find number 1, find the AP. That means give me the sequence, give me the arithmetic progression, give me the sequence, the arithmetic sequence. And then the second term said find the GP. And then the third question said find a new sequence. We don't know whatever is going to be the name given to this new sequence. Obviously, it's a combination of both an AP and a GP. All right. Now, this is a very interesting question. It tests your ability to interpret questions that has to do with AP and GP. So let's see how we're going to solve this. So you have to take it one step at a time and use all the data to get your answer. So I have a very important data here that told me that I get my term for my new sequence by adding the corresponding terms of the AP with that of the GP. All right. So that means I won't be wrong at all if I went on to say that, because I can see that they told me that my V1, which was the first term of the new sequence, was 8. That means I can go on to say U1 plus T1, U1 plus T1 is equals to 8, because obviously my V1 was 8. And don't forget, the first term of the new sequence is gotten by adding the corresponding terms of both sequences. That means AP and GP. So U1, don't forget, U represents AP and T represents GP. So when I added the two terms, I got 8. That's what they are saying. And another thing I can also add is that U3 plus T3 gave me 52. You have to pick things little by little. Once you do this, you will never go wrong. All right. Now, let me go on to try and bring a lot of insights to what we have right in front of us. I was already told the difference. of my common ratio, of my AP. The difference was given as 2. All right. Now, there's something we're going to be doing. Now, if I'm going to write my AP, I want to try and write what my AP will look like. I have my difference to be 2. If I decide to take, of course, I'll be writing the first term of my AP as AU, and I'll be writing that of a GP as AT, so that you won't confuse A for A. Don't forget, A for the AP is different from A for the GP. So AU will be my first term. My second term will be AU, that means the first term plus D, which was 2. So this is going to be my second term of the GP, of the AP rather. The third term will obviously be A plus 2D. And that will be A plus 4 because my D here is 2. So I'll be having A plus 4. Now, if you wanted to go on and on, of course, you will not need on and on because the only details I have here is that for the third term and that for the first term. So let me just stop here. Of course, this is how the AP is going to look like. All right. Now, we can go on to do that for the GP now. So let's try and find the terms of the GP. For a GP now, of course, the first term is still going to be AT rather, because the GP we're using T. So this is the first term of the GP. But how do we get the next term? We get the next term of a GP. Don't forget A, then next one will be A times R, then A times R square, and on and on and on. So in this next case now we have A times R. So that will be A times AT, that means the first term of the GP, times 3. That will be 3AT. Of course, the next term will be A times R cube. R square. R square here will be 3 raised to the power 2, which is 9. So the next term, the third term will be 9. Let me write the 9 properly because we are having 9, then AT. Looking nice, right? Looking at all these things, you have to just, it's quite very simple. You have to just be very patient with what you do. So what I'm trying to bring out here is that I want to find a way to talk about I want to use this thing. You see these things I have here, this interesting thing I have here. This is where my solution is going to come out from. So I want to, here we're just having U1 plus T1. I want to use the real terms. So instead of writing U3, because for me to be able to find the AP or the GP, I need my first term, I need my common ratio. That's going to give me my answer. So if I know my first term, I know my A, and I know I know my D and my R, then so I need to know my A. So to get my A, I need to make use of these particular expressions using the real values rather than just writing U1 or U3. So that's what I want to try and use. So let's try and now use what we have now. Don't forget, this was the third term. This here was the third term. This was the third term of the AP. This is the third term of the GP. So I'm sure you agree with me if I go on to write this particular equation, this one, if I write it as, if I don't write it as U3 plus T3 anymore, and I write it rather as U3, which was the third term of the AP, is A plus 4. So that will be A plus 4. Sorry, let me write this as AU, don't forget, AU plus 4. Then the third term of the GP, that will be 9AT. Can you see that? Now, I was told that this is equals to 52. This is the kind of question you should expect. This is a 2019 question. So you have to brace up for questions like this. All right. Now, pay real attention to what I'm going to do now. Of course, this is me expressing this one. I can also express this first one. Let me try and express this first one on top of this so that you can get the hang of it. U1 was what? U1 represented the first term. Now, this is the first term of the AP, and that's AU plus T1, which was the first term. I can write that as AT. And they said this was equals to 8. All right, so this is me. You see, I've been able to change the entirety of this particular equation now to this using the real terms now, no longer using U1 or T1. So don't forget, my aim here is to try and find the first term, because once I can get the first term of any AP and I know the common difference or the common ratio when you are dealing with GP, I'm good to go. I'll be able to get my AP and my GP. So the major thing I'm trying to do in all these things is to find my first term for the AP and first term of the GP, because I already know my common difference and my common ratio. So all I will be doing next after getting the first term is to just keep on solving with them. So this is the next thing to solve. Now, please pay real attention. I'm going to do something here. Look at something. You can see AU plus AT written here. AU plus AT is written here. Now, I want to find a way to solve this. Of course, I want you to understand that you can go on to make use of your simultaneous equation. It will work very much. If I decide to bring minus, of course, open this up, bring minus 4 here, it will work very much. Let me tell you that. You can use the approach of simultaneous equation. For instance, you can go on to make AU subject of formula. I'm repeating this now. You don't have to follow the method I want to use. You can make use of simultaneous equation. You'll be very good. That means I can make AU now subject of formula, and that will be 8 minus AT. And wherever I saw AU now, I'm going to be fixing that in. I'll get my values. You'll be very correct. So, but just for the sake of flexing some little mathematics muscle, let's do something quite nice here. I'll be changing this particular equation in a particular way. I'll write this as AU plus 4. Now I'm going to do something. I'm going to dissolve this to be 80 plus 880. That means, of course, I'm sure nobody argues with me that 180 plus 880 is not 980. It's actually 980. So all I just did was to dissolve it. And you'll be asking, why did I do that? I did that because I wanted to see, I'm trying to see AU plus 80 so that I'll just say AU plus 80 is 8. I was trying to do. So I just wanted to make that work so that I can make it easier for myself. So of course, I can bring this together. Let me just make it like this. Plus 880 equals to 52 minus 4. I'm bringing this 4 to this other side now, and I'm sure you can see AU plus 80 plus 880 here. So this, all this now, from what I have here, it's equal to 8. So I can write this as 8 plus 880 equals to, this will be 48, right? This will be 48. And sorry, let me continue it right here. I'll continue it here. So I have 8A equals to 48 is equals to 48 minus 8. That means 880 will be equals to 40. And I can conclude my my 880 now. Let me write that here. My 80, of course, will be equals to 40 over 8, which is equals to 5. All right. So now we've been able to arrive at a value for 80. Now, I told you already, whatever I did here, you don't have to follow that process. When you go to these two places, just make use of your simultaneous equation, you'll be good to go. Either using elimination method or substitution method, you are good to go there. What I did here was just my own, the path I decided to take. So now that I know that AU plus 80, but don't forget AU plus 80 equals to 8. So obviously, if I have gotten 80 to be 5, that means AU will be equals to 5 plus 8. Sorry, 5. AU plus 5 is equals to 8. So my AU will be equals to 8 minus 5, which is 3. All right. Now, this is the best thing that has ever happened to us in this particular question, is that I've been able to get my first term for both the AP and the GP. You see, after getting this, there's no other thing that can stop us from getting my AP, because I know my first term, I know my common difference. Now, I've gotten my first term for my AP, AU, that was AU, to be 3. So first term AU equals to 3. So if I've gotten my first term to be 3, of course, I know that I can get my second term. Let me write that somewhere here. So I've gotten my U1 represents, so U1 now, which is my first term, which is AU, is 3. So my second term, U2, will be AU plus D, which will be 3 plus my D being 2. That will give me 5. My U3, which is my third term, will be AU, that means the first term of this, plus 2D, which will be equals to 3 plus 2 times D, that will be 4. That will be 7. So getting these 3 terms, of course, is sufficient. You can go on to solve for more if you want to, but I can conclude now that for my AP, what I wrote here, rather than I have gotten my AP successfully to be 3, 5, 7. So my AP is equals to 3, 5, 7, ... So that's how we're going to get. I've gotten my AP already. As I told you, once I get my first term, I'm good to go. Now, the next thing to solve now is to get the GP. It's important to get the GP in this particular question now. Don't forget, for the GP, then the last question is supposed to be for us to solve for the new sequence. So for the GP now, I've gotten my first term for my GP to be 5, which was the UT, the AT rather. My AT, I got my AT, this is it right here. My AT was 5. So, and that was my first term. So this is for the AP. So for the GP, my first term for the GP, U2, sorry, I use T. So that will be T1, which is equals to AT, the first term for the GP in this case. I got it to be 5. Now, my T2 will be AT times R. Don't forget, that's how you solve for GP. I know my GP common ratio to be 3. My first term to be 5. That will be 5 times 3. That will be 15. So to get my T3, that's the third term for my GP, will be AT times R squared. That will be 5 times 3 squared. That will be 5 times 9. That will be 45. So this will suffice for us getting our sequence. So I can go on to conclude that for my GP, the sequence is the first term here, 5, then I have 15, then I have 45. So anybody that sees these two sequences can continue them. You don't have to. Of course, if you want to, you can go on to do for 4th and 5th term, but of course, I've already established a good relationship. It's very perfect for you. Don't try to stop at the second term, because something at the second term doesn't give you an opportunity to call whatever happened there a common ratio or common difference. So if you only did for 3 and 5, that means you have not established anything common, because it happening in just one situation doesn't mean it's common. But when you said 3, 5, 5, 7, that means you are saying you can see a common difference now of 2, and then you can see it also for the next one. So you have established your common difference. So it's the minimum of the number of terms you should always give when you're told to give an AP or a GP is 3. Of course, you can go on to do for more, and anybody that sees this now can commit to the next one. If this was 3, this was 5, 7, the next one will be what? 9. Next one will be what? 11, because you are adding a value of 2 to each of them. Same thing goes for the GP. You cannot talk about the common ratio if you have not identified at least 3 terms in the particular sequence. So in this case, now you can see that there's an established ratio already, because I see that 5 times 3 gives me 15. 15 times 3 gives me 45. So it's a common ratio because it happened on at least 2 graphs. So you can go on to make the next one as 45 times 3, which will give you on and on and on and on. You keep going. So now the last question here said we should find the new sequence. How do we find a new sequence in this particular question? A new sequence now, we're told that to find the new sequence, this is it right here. The new sequence was adding the corresponding terms of both the AP and the GP. So in this case now, what's the first term of our GP and our AP? So we have 3 and 5. So that means for my new sequence, which I can call V1, will be equals to U1 plus T1. That means the first term of the AP plus the first term of the GP. In this case, the first term here is 3 plus 5. This is 8. Now for V2, which is the second term of the new sequence, I have U2 plus T2. That means the second term of the AP plus the second term of the GP. So in this case, we have 5 plus 15, and that will give me a value of 20. Of course, you don't want to end at just giving 2 terms. You want to give at least 3 terms. So V3 will be equals to U3 plus T3. That will be the third term of the AP plus the third term of the GP. In this case, we have 7 plus 45. And that gives me a value of what? 52. So you can see that we have been able to consume these whole questions, and we have been able to get the 3 questions that was asked us. Number 1, we're told to find the AP, then we're told to find the GP, then we're told to find the new sequence. This gives me my value for the AP, this gives me my value for the GP, and these are my values for the new sequence. All right, so this is 2019 question. I believe a theory question. This is the C of a theory question. I can't really tell right now how many marks it did carry, but you can see how substantial this is. This is the kind of questions you should expect while preparing for your exam, especially when you're dealing with sequence and series. All right, so I really feel we have done so much. I want us to complete this class by talking about harmonic sequence, which will be the last discussion on the basis of sequence and series. So I feel I've been able to establish a lot of points in the mind of whoever has been following, and I'm very sure this should you should have increased your knowledge on sequence and series through this tutorial. So let's end up this class with this last section on harmonic sequences. All right. So what is harmonic sequence? How do we identify harmonic sequence? How do we know something is an harmonic sequence? And what gives us that clue? Harmonic sequence is probably the simplest of them all. It's so simple. I do not expect any complexities. And if you had complexities before, I really hope after now you don't ever have it again. All right. So now when you're dealing with harmonic sequence, what you need to know is the harmonic sequence and arithmetic progression, which is AP. I told you already that another way of identifying AP is linear sequence. So if you see linear sequence somewhere, don't be confused. It's still the same thing as AP. So harmonic sequence and AP, they flow hand in hand. So the reciprocal of an harmonic sequence will always give you an AP. Let me say that one more time. The reciprocal of an harmonic sequence will give you an AP. So an harmonic sequence is a special type of sequence whose reciprocal form an arithmetic sequence. Just so you understand quickly. If we're going to talk about an AP, we said an AP was given, the terms of an AP, we said it was given as UN equals to A plus N minus 1 times D. This was what we said, did we not? Good. Now, when you're talking about harmonic sequence is generally just, let me identify harmonic sequence as Vn. Harmonic sequence is 1 over A plus N minus 1D. All right. Like this definition, you have to be rigid with it. So once you see that the denominator 1 over, I did not say anything, I said 1 over, so you have to be specific. It is 1 over a particular arithmetic sequence. Let me give you a very quick example, a very basic one. So let's take, for instance, I have my AP as 2, 4, 6, 8, 10, 12, and so on and so forth. The corresponding harmonic sequence that can be derived from this particular one will be 1 over 2, 1 over 4, 1 over 6, 1 over 8, 1 over 10, and on and on and on. This is just the basics of harmonic sequence. All you need to remember in harmonic sequence is that the denominator of an harmonic sequence will form an AP. The denominator of an harmonic sequence will always form an AP. So whatever you've known about an AP, all you need to do is just bring it back to a situation where you had 1 over that. So there are many questions that used to come out in this sense where, or probably some questions may come out in this sense that would ask you to identify if this particular sequence is harmonic or not. Of course, how you need to tackle questions like that is just to ask yourself, is this particular question, does the denominator of all the sequence, does it form an AP? Of course, you remember that an AP has a common difference. So once it has a common difference and you can relate that to an AP, then it is an harmonic sequence. But in any case where probably one or two of those terms do not establish an arithmetic sequence, I mean the denominator, you cannot call that an harmonic sequence. So let's see some few examples. Imagine you have this question that you have 1 over 11, and you have 1 over 14, then you have 1 over 17, then you have 1 over 20, and on and on and on. So the question goes for you to identify if this is an harmonic sequence or not. So let me quickly warn you that the fact that it has 1 over doesn't mean it's an harmonic sequence. Please take note of that. An harmonic sequence doesn't literally mean that you have to have 1 over something. It has to be that it has to be 1 over number 1. Then it also has to be an arithmetic progression on the denominator. So we have seen that all this has 1 over, all right? That first fact is noted. The next thing we then need to go on to prove is, does this follow an AP? All right, let's try and see what happens here. Can we find, if we have our A to be 11, and we said our A plus D is 14. Of course, in this case, we will be saying 11 because A is 11 plus D equals to 14. D here is equals to 14 minus 11. D here is equals to 3. So the difference between these terms was 3. Let's see, could we establish that 3 on every of the terms? Go on and check. 11 plus 3, 14. 14 plus 3, 17. 17 plus 3, 20. Perfect. This is an harmonic sequence. So we'll take this as an harmonic sequence. Of course, because we have been able to establish that the denominator follows the pattern of an arithmetic progression. Let's see this particular question. We have 1 comma 1 over 2, 1 over 2, 1 over 4, 1 over 8. One over 2, 1 over 4, and 1 over 8. So is this an harmonic sequence? That's the question you should ask yourself. So is this an harmonic sequence? All right. Now, I understand that some of you will say, oh, we cannot see 1 over in the very first value. Please, that's not going to be the basis of which you're going to disqualify this as an harmonic sequence, because you can easily write 1 as 1 over 1. So the fact that you saw 1 as the initial something doesn't necessarily mean it's not an harmonic sequence. You have to go on to then try for if the denominators are going to form a arithmetic progression. So let's see the denominator we have here. We have the denominators, we have 1, we have 2, we have 4, we have 8. So we have 1, we have 2, we have 4, we have 8. Anyway, I will tell you, I will submit to you that without even working anything, I can see this will not give me an harmonic sequence. So let's try and see. Let's find for the common difference. So let's do 2 minus 1. Of course, D will be equals to T2 minus T1. Or I think you are used to using U. So let's use U here. That means the second time minus. And then D is supposed to also be U3 minus U2. D is also supposed to be U4 minus U3. So let's see what was our D on this basis. D 2 minus 1. 2 minus 1 gave me 1. D on this basis 4 minus 2 gave me 2. D on this basis 8 minus 4 gives me 4. This will never be an harmonic sequence. It doesn't just even have one conflicting. It has every one of them. There's actually no even difference that actually aligns with each other. So this is how you identify a harmonic sequence. Let's take this very last sequence and see if we're going to be able to. Oh, we still have 2 more sequence to identify if it's harmonic or not. Of course, this will solidify your knowledge on harmonic sequence. You're supposed to always be able to identify an harmonic sequence. So we have 2 comma 1. We have 2, we have 1, and then we have 2 over 3. Then we have 1 over 3. We have 2, we have 1, we have 2 over 3, and we have 1 over 2. I'm sure. Let's try and examine this. One of the definitions of harmonic sequence is that the reciprocal of an harmonic sequence should give you an AP. So let's try and find the reciprocal of this term, and let's see what we're going to get. What's the reciprocal of this term? The reciprocal of this will be 1 over 2, 1, 3 over 2, 2 over 1. You understand from the definition, we said an harmonic sequence is a sequence in which the reciprocal will give you an arithmetic progression. And if you're asking how I got these values, I just did the reciprocal of all these values. The reciprocal of 2 is 1 over 2. Reciprocal of 1 is 1 over 1. Reciprocal of 2 over 3 is 3 over 2. Reciprocal of 1 over 2 is 2 over 1. So let's see, does this give you an arithmetic progression? Of course not. This will give me, or let's see. What is 1 minus 1 over 2? 1 minus 1 over 2 gives me 1 over 2. Okay. What's 3 over 2 minus 1? Okay. And what is 2 minus 3 over 2? Do you see something right here, guys? This is an harmonic sequence. This is an harmonic sequence. And it's quite important to take note of what really happened here. That by looking at this, if you make a conclusion quickly, you would have gotten it wrong, because if you omitted the definition of harmonic sequence in this particular question, you would have gotten it wrong. Looking at what happens there, the first thing I wanted to look at by default was to see if we're going to be getting 1 over this. But of course, because 2 doesn't have 1 over, you will probably want to make a conclusion on that. But don't forget, that was not the basis that you define an harmonic sequence on. You define it as a sequence in which the reciprocal will give you a AP and AP. So every one we have done, if you do the reciprocal of this, if it doesn't give you, of course, some are more easier to solve. Let's see. This particular question we solved, we can go on to try and investigating it much better than what we did here. Of course, it's not an harmonic sequence, but imagine we wanted to solve it using this particular method we're using. You can go on to do the reciprocal of this. This would be 1 over 1. This would be 2 over 1. That's 2. This would be 4 over 1. That's 4. This would be 8. So if you go on to use this, you will see that we did. Of course, that was what you see what we got here. You can see that this will not give you an harmonic sequence. But if you looked at this and you try to use your 1 over to do this, you'll be wrong. What you needed to do was to go on to do the reciprocal. Guys, I want you to really pay attention to this. This is a very important question that can confuse students. So you see this question right now, it's actually an harmonic sequence. But if you're not very careful enough, you will not be able to identify it. Don't forget, I define an harmonic sequence as a sequence in which the reciprocal gives you an AP. So when I saw this question, I almost concluded it's not an harmonic sequence. But when I went on to investigate using the definition, I discovered that the reciprocal of 2 over 1, this is 2 over 1. 2 over 1 was 1 over 2. Reciprocal of 1 over 1 is 1. Reciprocal of 2 over 3 is 3 over 2. Reciprocal of 1 over 2 is 2 over 1. All right. By default, if this is an harmonic sequence, this reciprocal is supposed to be an AP. All right. Let's try and investigate on this. Let's find D. The D being U2 minus U1. And then our D also must be U3 minus U2. Our D also must be U4 minus U3. If all these D's are the same thing, then this is an AP. If we're able to get a common difference, then it's an AP. So let's go home. 1 minus 1 over 2 gives me what? Of course, 1 over 2. Go home to find 3 over 2 minus 1. What does it give you? Find out it will give you 1 over 2. Then go on to find 2 minus 3 over 2. It will also give you 1 over 2. Now you can see that there's an established common difference between this sequence, this AP. So this is an AP already. And since the reciprocal rather of this particular sequence gives me an AP, I can conclude perfectly that this is an harmonic sequence. All right. I love the fact that we tackle this question so that you don't get confused with questions like this. So let's try and see another question. The last one right here, we have on identifying an harmonic sequence. So look at this question. We're given 4 whole number 1 over 4. And we're given 4 whole number 1 over 2. And we're given 4 whole number 3 over 4. And we're given 5. So the question is still the same. Is this an harmonic sequence? This is what we are asked to do. So I would love you to make an attempt on this before I do. Quickly prove that. Is it an harmonic sequence or not? So from the questions we have solved, we got the first question to be an harmonic sequence. We got the second one to not be. We got the third one to be an harmonic sequence. And now we're here with the fourth one. Let's examine if this is going to give you an harmonic sequence. So I want to first of all go on to make all this up to their improper fraction. This will be 16. This will be 17 over 4. 17 over 4. This will be 9 over 2. Sorry, was that? Okay, that was 2 there. Okay. And now we have 19 over 4. And then we have the last one as 5. All right. This was the sequence we were given, and we are asked to investigate if this is an harmonic sequence or no. All right. So what I have to do is to go on to find the reciprocal, because don't forget the definition of an harmonic sequence is that its reciprocal is an AP. If its reciprocal is an AP, then it's an harmonic sequence. So let's find the reciprocal of this particular sequence and see what happens there. So we have 4 over 17. We have 2 over 9. I'm sure we understand how to find reciprocal. That's just reciprocating it. So reciprocal of 9 over 2 is actually 2 over 9. Reciprocal of 19 over 4 is 4 over 19. Reciprocal of 5 over 1 is 1 over 5. So I want to go on to find out if this is an AP now, because these are the reciprocals on the basis of the sequences we had before. So is this an AP? All right. If it's an AP, there's something that must happen. The differences must be common. So that means my difference should be equals to the second term minus the first term. My difference should be equals to the third term minus the second term. My difference should also be equals to the fourth term minus the third term. If any of these rules are breached, it's not a common, it's not an AP. That means if this two works and this doesn't work, it's not an AP. The three must have the same value. So let's go on to find out what is U2 minus U1. That means you can use, you can have this on your calculator if you want to. What is 2 divided by 9 minus 4 divided by 17? Of course, the value here was minus 2,153. Don't make your conclusion on the basis of a negative value. It's not a yardstick. So let's go on to do 4 divided by 19 minus 2 divided by 9. Of course, you can see what happened here. I got minus 2 over 171. Now, if I was in an exam hall and this was an objective question, at this point, I would stop working and conclude on my result, because I know already that even if the last one gives me one of them, it will not still be an arithmetic progression, because it has to align all together. We have to have a common difference. So what we have here, the last one, just for the sake of working, we have 1 divided by 5 minus 4 divided by 19. And I have my value to be much more even diverse again. I have minus 1 over 95. So from what I can see right here, I don't even have a common ratio, common difference at all. So I can conclude that this particular sequence that was given here is not an arithmetic progression. So we don't have an arithmetic, we don't have this as an AP, and so therefore, we don't have this as an AP, and so therefore we don't have this as an harmonic sequence. All right. So we have a question to solve on harmonic sequence. Let me try and shoot it out and see what you're going to do with it. So we're told to find the 10th term of this harmonic sequence. I'm sure everybody here can get this answer. 1 over 8, 1 over 12, 1 over 16. This is not something you have to waste time on. 1 over 8, 1 over 12, 1 over 16. So we are supposed to find the 10th term. Find 10th term. You don't need to spend much time here. You have to find the 10th term of this particular sequence. How do you go about this? Of course, since they've told you it's an harmonic sequence, so you already know that the denominator will actually be in the form of an AP. All right, let's try and see the AP here. We have 8, 12, and we have 16. The only thing I will be trying to find now is to find the 10th term of my AP. So I know my A. What's my D here? You can find your D by doing 12 minus 8, which is 4. 16 minus 12 is 4. So my D here is 4. Now, using my general formula, my T10 or my U10, depending on how you decide to write that, my 10th term will be A plus 9D. A plus 9D. And A is 8 plus 9 times what? Times 4. That will be 8 times 8 plus 36. That will give me my total value, my final value to be what? 8 plus 36 should give me a value of 44. So this is my AP. My AP was 44. So I can go on to conclude that my 10th term will be 1 over 44. Because, of course, if this was my 10th term of my AP, my 10th term of my harmonic sequence will be the reciprocal of this, because the reciprocal of an harmonic sequence gives you an AP. So you can see that the reciprocal of this will obviously give you 44. So that's how we get this. Quite simple and straightforward. I'm sure everybody can understand this. Okay. I would be giving you, or you know what we're going to do? The rest questions that we have on harmonic sequence, we will move it forward to our 9 o'clock class. So we'll be solving more questions on harmonic sequence in a class probably today or tomorrow on Sunday. I would love us to stop this class at this point. I really feel I've been able to pass a very great message to you guys when it comes to sequence and series. I really hope you guys are much more grounded in this topic. I feel we have done justice to this topic. We studied more of geometric sequence in this class and harmonic sequences, and I really hope you enjoyed yourself. So we'll be ending the class at this point. I hope to see you by 9 p.m. where we'll be solving loads of questions, past questions on several topics, A-level topics. All right, guys, thank you very much for joining. I hope to see you by 9 p.m. Bye-bye.